Well, thank you, Sam, and others involved who I don't know, for organizing this meeting and for inviting me here to speak about this subject. This is my title, which will become clearer as we proceed, especially towards the end. And I'm, as I said the other day at the Raman Institute, I'm from the University of Bristol. There are 29 Bristols in North America, one of which, Bristol University, existed for a short time and then went bankrupt. So we are told we must say University of Bristol, not Bristol University, whose website says, don't send your children to Bristol University because it's financially unsound. So my Bristol is the Bristol in the European Union, at least until next Thursday. Right. Now, we had many years ago a comedy show in the UK, Monty Python Flying Circus. And they always began by saying, and now for something completely different. And I will just, it's really interesting. The lovely lecture you've just had from Professor Mukunda is very different from what I'm going to say. And it illustrates something that I think Feynman said. And you know, if you quote Feynman in a lecture, nobody dares to disagree with you. And he said this, how wonderful it is in physics, you can look at the same thing from several different viewpoints. So I will illustrate this, although I didn't realize until I heard the lecture preceding that this is indeed the case. Now, for a number of decades, I didn't speak about the geometric phase because it became popular in the 1980s, and in the middle of the 1990s, I decided I'm completely sick of it. I will never speak about it again. I will do completely different things, which I did. But I've come back to it, and there are a number of reasons. There's a main reason being there's an unsolved problem remaining, which I'll discuss towards the end, but also because the subject continues to have applications in different areas. Condensed matter physics in particular will be discussed here. I look forward to learning a great deal because I've deliberately in my entire life avoided condensed matter physics. So I will be interested to hear about these applications. But one of the reasons for being interested in the geometric phase is that it connects a number of different areas. And I want to quote my very distinguished predecessor in Bristol, Charles Frank. And he said, very profound thing during his retirement speech, he said, physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. That's a very deep remark. Connections are not optional extras in physics, they're an essential part of what we do. So that's one theme. Now, the talk will be a kind of sandwich. The bread, the beginning and towards the end, will be rather non-technical, indeed very non-technical. Material I will give in a public lecture, but I want to give it. In the middle, there's a section which is rather technical. So this is, so you know what to expect. Now, I will hardly mention, during the main body of the talk, the names of people. I will deliberately not mention the names of people. I will speak about ideas. I will mention one or two people, but mainly not. However, towards the end, I will give a timeline, my view of the rather intricate and subtle history of the development of this concept. But so names will come. In particular, one will occur to you repeatedly. I will not utter the name, but then it will come. Good. But I begin with a name and with some history. The first geometric phase discovered in 1830 in the optics of crystals. And I want to emphasize it for a number of reasons. By Hamilton. Here he was. And he was, you know, he taught us about phase space. It always seemed to me rather artificial, it does to any student at the beginning, that you treat momentum and position similarly. They seem so different from each other. And anyway, momentum, which in many cases is just direction, often seems irrelevant because in many cases, the forces in optics or the determinations of forces in mechanics and determination of rays in optics don't often involve direction. But in the optics of crystals, they do. And that's one reason why Hamilton, in the first application of his ideas of phase space, was interested in crystal optics. Now, very quickly I run through this standard material. In a general crystal, two beams of light with different polarizations travel in any direction. And their speeds were described by Fresnel's wave surface, actually it's two surfaces, that intersect at 2 points on two optic axes. The wave surface is a polar plot in the direction space of the two refractive indices. Now, Hamilton discovered this shape for the most general crystal. It wasn't understood by Fresnel that what his surfaces actually looked like. And he noticed there were two directions, two optic axes, and therefore this were called biaxial crystals, 4 intersections. And where the two polarizations have the same refractive index. Now we know it's the degeneracy of a matrix that comes from Maxwell's equations. Good. He understood each intersection is a double cone, and it's the first conical intersection in physics, which anticipated others in quantum chemistry and in condensed matter physics. They all have the same mathematical origin, degeneracies. One of the bees in my bonnet is the term that people often use, Dirac points. They're not Dirac points, they're Hamilton points. Dirac, who we admire infinitely in Bristol, he was born there, educated there, never talked about a cone in this context, and he never drew a picture of a cone. And all of the reasons, we can talk about it later, why these things are called Dirac points are actually anticipated in Hamilton's 1830 work. This nice shape, by the way, wave surface, I had the pleasure of inaugurating a couple of years ago this nice sculpture in Dublin, TrinityCollege, where Hamilton worked. Now, he wanted to see this conical intersection in physics, and he did. He had a slab of biaxial crystal cut at right angles to one of the optic axes, and he shone light in, or he predicted what would happen if you shone light in. The light would expand into a cone, a slant cone, it doesn't matter why, and then it would refract out into a hollow cylinder. And he said, if you put a screen there, you should see a bright ring. Well, this was done. Actually, there are 2 rings, not one, which you didn't know. The experiment was done by Humphrey Lloyd. It created a sensation for reasons I'm not going to discuss now. And what Lloyd realized, and this is the point for today, is that the rings are linearly polarized, and the direction of polarization rotates by pi as you go around. Now, I think this is the first geometric phase in physics. It's a phase change of pi. Now we know that these polarization directions are the eigenvalues of a little matrix. Position on the screen is a parameter. You go around and you surround a degeneracy, and you get a phase change of pi. It's a real symmetric matrix. So that's the first. So this is what I wanted to emphasize at the beginning. Now, phase. You know, there are different meanings of the word phase. I once had a student, not a good student, I should say, and first year, who had learned about the phase change of pi on reflection. And she asked me, does that mean the light actually boils? You know, different meanings of the term phase. But it describes a stage of any cyclic process. We all know phases of the moon, which is a cyclic change in the shape of the moon. Of course, phases are described by angles. We all know that. Very good. Now, geometry. Geometric phase. We have geometry. The underlying mathematics, in one way of looking at it, is parallel transport, goes back to Gauss, parallel transport in the presence of curvature. And you probably all know this little demonstration. You stand at the North Pole with a javelin, here it is, pointing forward, here's the center of the Earth, and you transport it. You go down to the equator, and then you go round towards the east pole, and then you come up again. And at every stage, you're never rotating about the local vertical, never, about the radius vector. Nevertheless, although you never rotate, the javelin does turn, and when you come back, it's pointing in a different direction. What is that change of direction? It's a solid angle of the path. It's the area on the sphere, which is a curved surface. Very good. There it is. It's global change without local change. You're never rotating, but you turn. Okay, good. And you all know, I'm sure, the Foucault pendulum, which swings back and forth, but its plane of swing turns as the Earth rotates beneath, and after 24 hours, the plane of swing has not returned, although it never twists about the local vertical. So that's the non-local, that's the parallel transport, but it's the vertical about which it swings has been transported, and the angle, it's a solid angle again, 2 pi times the sine of the latitude. If the pendulum is a conical pendulum, then you simply can ask, where is it at the end of this 24 hours? Well, you might think that you simply add up all of the angular velocity times time, actually constant, not in general would be an integral that will predict something, which is wrong. There's this additional angle which is the same. It's this solid angle of transporting. Now, underlying this is a still more general idea, anholonomy, which mathematicians miscall holonomy, okay? Something returns after a cycle, position of the javelin, the pendulum axis, the local vertical, and something else does not return. The direction of the swing of the direction of the javelin, the swing plane of the pendulum. There are a number of examples of anholonomy. One of them is the falling cat. You all know the cat. You drop a cat and she has 0 angular momentum, and always has, because there's no torque on her, so she doesn't rotate, but she turns. And she does that because of, she's not a rigid body, she cleverly deforms her body. In the space of shapes, she makes a circuit, she has the same shape at the end and at the beginning, more or less, but although she has never rotated, she has turned. Okay, very good. Another example, when you park your car, it often happens, you have 2 cars close together and you try to park and you find that you're some distance from the curb. Then you make a series of maneuvers, surprisingly many you need, periodic maneuvers, cyclic maneuvers consisting of driving and steering, at the end of which each one you're a little bit closer, a little bit closer. Driving and steering, this is the maneuver that you make. The order matters, by the way. If they commuted with each other, you could do all the steering in the garage before you left home. Okay, very good. So you make this series of maneuvers, and you're a little bit closer every time. Now, drive and steer. In the space of drive and steer, this little anholonomy, this sideways shift, this lack of return, is an area. And that's why, if you have a space of epsilon, if you really have 2 close cars, the number of maneuvers you need to make is 1 over epsilon squared. It's many more than you think. We all experience this, familiar with it. Very good. Now, the geometric phase combines these 2 ideas, phase and anholonomy, in the physics of waves, optical waves, quantum waves, other waves. Now, the phase is the phase of waves as they oscillate. Now, you know, waves are one of the great themata of physics. So it's important to understand everything about them, and the characteristic property they have is phase. So we should understand phase. The anholonomy is used cyclically and slowly, later we come to this, much later, change the conditions of the waves while they're oscillating fast. And in light, this could be changing the state of polarization or changing the direction of the light. In quantum waves, cyclically changing the forces that act on molecules, atoms, electrons, neutrons, whatever. Now, dynamical and geometric. Even if you do nothing, waves wave, okay? So if you do nothing, then after some time, there will be a large, if you do it slowly, a large number of oscillations. In this case, 10 in this cartoon, okay. However, the geometric phase, when you do something to the system, something cyclic, is an additional phase. It's a consequence of the change. So here you have 12, so the geometric phase is 2 more oscillations, is 2 pi. Very good. So you think of it this way. After the cycle, again I'm thinking slow, the dynamical phase answers the question, how long did your trip take? And the geometric phase partially answers the question, where have you been? Okay. Now, one way to measure geometric phase is by interference. These examples I'll give are rather old. I'll be very quick about it. In polarization optics, you can you can have a sequence of polarizers in an interferometer. You will see fringes. Very good. You have a stack of polarizers. Here are some fringes, and this is a compensator to make sure that you get good contrast to keep the intensities equal. Very good. Now, if you twist the polarizers, you can shift the fringes by the geometric phase, and states of polarization are points on the Poincare sphere. And here it is. You all know North Pole is circular one way, South Pole the other way, linear polarizations around the equator, and any cyclic sequence of elliptic polarization. In the beginning of this story, many people use sequences which are geodesics on the Poincare sphere, but you don't need to, actually. What I'm going to describe is 2 cases where they aren't geodesic, they cycle like this, and the geometric phase is half the solid angle. Very good. So here's an example. You have a twisted stack of 4 polarizers. The geometric phase is predicted to be pi for this particular case. And you see, if you untwist and then you twist, you get this phase. And the scale is millimeters here. So these are kitchen tabletop experiments. Here's a twisted stack of 4 retarders. The geometric phase predicted to be pi on 3, and indeed, so it is. Polarizers are projection operators, and retarders are unitary operators, but they're transparent, but the concept is the same and the formula is the same for both those cases. They're mathematically very different types of procedure, but the geometric phases are the same. A different type of polarization optics is in a coiled optical fiber, where you can control by the coiling the local direction of the light, and you arrange it to be in the same direction afterwards as before, and you send in polarized light. Let it be linearly polarized, it doesn't have to be. You send in linearly polarized light, back comes light polarized in a different direction. The polarization has rotated, although it's been parallel transported. We come to that much later. And the rotation of the polarization is the solid angle of the unit tangent on the sphere of directions during this process. And the experiment was done, solid angle versus polarization rotation, for a number of different sorts of cyclic rotation. It doesn't matter, you can have it rotating fast here and slow here, you can, depending on how you twist the optical fiber. In quantum physics, you could do the same thing with spinning neutrons, which couple to a magnetic field through their magnetic moment, and you have coils which can change the magnetic field around a cone. And once again, the geometric phase is half the solid angle, and there's a peculiar way of presenting the data. A difficult experiment at that time, 1980s, but it works. Another example is the Aharonov-Bohm phase, about which I shall say a little bit more later. I give a whole lecture about this, so I'm just being very quick and, at this moment. So here you have 2 beams of electrons which are separated, and then brought together again with magnetic lenses in the electron microscope, for example. And of course, you get interference. It's an example of 2-slit interference. The interior of the region is not reached by the electrons, but you put magnetic flux there. Magnetic flux has a vector potential. This affects not the trajectories of the electrons, but their phase. and the fringes are shifted by the geometric phase, which is equivalent to taking electrons in a box and transporting them around the flux line. And again, it's the phase from the geometric phase formula is the same as the phase that Aharonov and Bohm had predicted earlier, before phasey ideas became popular. Very good. And this experiment was done, fringes without the flux. When you put the flux, you shift the fringes. It's not so easy to measure a shift of fringes. So one thing you can do is to change the, along the magnetized iron fiber, you can change the flux along the fiber, change the magnetization. So the fringe shift is different at different heights, which means the fringes will be tilted, as indeed they were, a tapered whisker. Good. Now, geometric phase from transport round a circuit can be expressed as a flow through the circuit. And this is a common idea in physics. You all know Faraday's law. You change the flux of magnetic field through a circuit and you generate a voltage around the circuit. The geometric phase, the fundamental flux quantity is curvature. And that, of course, generalizes what we saw in the beginning with the sphere. Very good. And in Aharonov-Bohm, the curvature is a delta function. It's concentrated on the magnetic flux line. But still, there is a flux of something, and the geometric phase can be interpreted that way. Good. Why is it geometric? Because it's independent of many things. Wavelength, particle mass, Planck's constant, magnetic field strength, depends only on the geometry of the circuit and on what is being transported. Now, this robustness could be helpful, people claim, in quantum computing, because you want to preserve phase coherence as much as possible to avoid decoherence. Doesn't avoid it completely, but at least some independence on parameters is useful. But topological. When I wrote my paper, the first draft of it, I'd said topological phases. My colleague John Hannay said, no, you mustn't call it topological because it isn't topological, it's geometric. He was right. But it sometimes is topological if the phase, it's geometric if the phase can take any value, solid angle, and if it depends on the circuit. Topological if the phase is independent of the path provided it encloses something, like the Aharonov-Bohm phase, which you enclose flux, provided you don't go many times or avoid the flux, then the phase is the same, independent of the shape of the path, or the pi phase when you include a degeneracy, as in that original example with Hamilton, the conical refraction phase. So they are topological. Now I'm going to give you, I'm going to mention a name now because it's my colleague, John Robbins. Some of you know him. I think this is actually the deepest application of phase ideas, in my opinion. And it's this, it's to understand the Pauli exclusion principle. Well, it underlies, I don't need to emphasize it here. It underlies chemistry, impenetrability of matter, electrical conduction, whatever, and no two electrons occupy the same state. It's a special case of the spin statistics connection. If you have particles with spin s, integer or half integer, and you exchange them, you get a sign -1 to the 2s, which is, of course, an integer. And if s is a half, then it's the Pauli sign. Good. Now, this applies to absolutely identical particles. And if you want to understand it, you need to understand identicalness in quantum mechanics, which is a deep and subtle thing. And we introduced a new idea into this old subject. First of all, how do you know that two things are the same? Well, you exchange them and you see what's different, okay? Well, every exchange is accompanied by a hidden rotation. I'm going to give familiar demonstrations, but I want to be rather careful about the logic of what I'm describing, and then I'll make the connection with phase. So I have two electrons. Here they are, this one and this one, and I reveal what is happening because I'm connecting them. So here they are. Now, when I exchange them without turning them, I find I have a twist, and it can be undone by rotating any one of them by 2 pi. So, exchange is, here's another way to see it. If you have an elastic band around your fingers such that the 2 strands are crossed, they're exchanged, when you look on the other side, you always find a rotation. It's unavoidable. You don't always see it because you don't always have this, this connection, but it is. So exchange of 2 particles is like a twist of one of them. So, to understand exchange, you have to understand twists. You've reduced the 2-body problem, or more generally N, with permutations, to a 1-body problem. You have to understand twists. Okay. Now, change of 2 particles is like 2 pi rotation of 1. Good. So without untwisting, you can't undo 1 term. But the surprise, which was demonstrated first, I think, by Dirac and then by Feynman, who used to like it, and so is that 2 terms can. And I want to illustrate that. So let me see if I can do it. So here we are, and I have half a twist, 1 twist. Now, without untwisting, nothing I do can remove that twist. It's still there. There it is. But now let me do 2. A half, 1, 1 and a half, 2. It's even more twisted. But now, I always forget to do, sometimes I do this the wrong way and it's worse. No, there it is. So it's, however many times I do this, it always seems miraculous that 2 is equivalent to 0 when it comes to twists. Now, mathematically, you're interested in thinking, how does this conjuring trick in macroscopic 3-dimensional space show itself in quantum physics? Well, in quantum physics, you represent states of particles by wave functions and numbers. So what is it that is different when you do it once, but not when you do it twice? And of course, it's multiplication by -1. So rotation 1 of particle, which is the same as exchange of 2, is like multiplication by -1, and that's Pauli. Now, what does this have to do with geometric phases? Okay, it has the following to do with geometric phases. Think of 2 particles at positions r and -r. You don't care where the center of mass is, so let it be the origin. Okay. Now, exchange is r goes to -r, and if the particles are identical, you really want to identify the positions r and -r in the space. This is an old idea. A number of people thought of it long ago. So you have r, you have -r, and you want to identify them. But if you really want to, if the particles are really distinguishable, you also have to identify the spin states of the particles. Now, that required some technology because normally the representation of spin is in a fixed basis. You look at the components, amplitudes of the components relative, let's say, of the z components along the z-axis. But in order to do this, you have to have a representation of spin which involves position. So you have to transport the spin from -r to r and identify. Otherwise, you haven't really incorporated identicalness properly. Well, that's what we did. It requires some technology, and it's not obvious you could do it, but you can. So you have a formulation where the spin automatically gets exchanged as the particles do. And then when you do that, you change the topology. The sphere is a projective plane, so that if you identify, one way to do it is you have the hemisphere, and whenever you reach the equator, you go to the antipodal point on the equator and then continue. And then, of course, exchange is a non-contractible loop in the projective plane. And once you've included this transport of the spin states, you then find that you get a topological phase of 2 pi s. And of course, that's exactly the spin statistics phase. This is not contradicting the field theory demonstrations. It's a different way of looking at it. Now, why is it that Robbins and I are not famous for having proved the Pauli exclusion principle? The answer is, as we subsequently discovered, there are different ways of incorporating this spin transport, and some of them give the wrong sign. They don't give the Pauli sign. Now, all of those other methods that we found, there's something wrong with them, something unsatisfactory about every one of them except the initial scheme that we had. So one of them only works for spin half. I mean, I don't remember, but every one of them, there was something unsatisfactory, but we were never able to find a clear mathematical specification of naturalness which would reinstate the one we first thought of as being the way, general and for all spins and all number of particles, because it also involves permutations when you have more than two. So that's why we don't say that we've proved the spin-statistic connection. What we say is we've given some insight into why it's true. Okay, so that's that. Now, that's the first bread of the sandwich. I told you now we have something technical, and for people deprived of formulas, I will give them. I'm thinking, and later I'll discuss other ways of looking at it, by thinking of a Hamiltonian involving parameters. So I'm thinking of parameter space, not the Hilbert space. Well, you have a Hamiltonian depending on parameters, and you force those parameters to make a circuit, right? So if you do it slowly, you have an adiabatic theorem, then the state comes back up to a phase, of course, and the phase is echoing, but differently described because it's parameter space, not projective Hilbert space. What we learned from Professor Mukunda, that you can either represent the phase as the integral of one form, or as the flux through the circuit of a two form, the curvature. And the nice thing about the curvature is that it's, unlike the one form, is that it's gauge invariant, and you can show that by transforming the derivative, the change of the phase, into a change of position in the, into a change of the Hamiltonian. And here it is. You're expressing this into, this is for the nth state of some Hamiltonian. You're expressing this in terms of all of the states that you're not transporting or you're not thinking of, and you have these energy denominators, and that means that when you get a degeneracy, this becomes very large, and that underlies all of these solid angle formulas. So singularities, degeneracy. I have to say, when I wrote my paper, I was most pleased with identifying the curvature as a fundamental quantity, because this echoes history. You know, before Faraday and Maxwell, you had interactions between charged particles, right, non-local. But then Faraday had, well, imagine that there's something, let's call it a field, just sitting there, existing in the space from sources, whatever, waiting to be activated by putting a charged particle there. Well, this curvature is like that too. It lives there in the parameter space, different for each state of particles, waiting to be actuated in the form of a geometric phase by a cycle in that space. So it's a similar idea. That's the curvature. I want to tell you a new calculation with Pragya Shukla. It's something we published in 2 papers recently. One long, one complicated, and one realizing it a little bit simpler. There's a lot of study now of phases and other quantities in disordered materials. And this involves randomness. And we wondered, what is the typical behavior of this curvature? Random parameter-dependent states. And what's the probability distribution of this curvature, two form, for an ensemble of physically reasonable ensemble of states. And before I do that, you did. Of course, two-form depends on the parameters. It's the simplest way to bring out its full structure is to have three parameters, because degeneracies are codimension 3 for general, that's the Wigner von Neumann theory, for general Hermitian matrices. So we have an ensemble of 4 matrices, n by n. Each of these is a matrix from the Gaussian unitary ensemble, which is the democratic ensemble natural for the simplest for describing random Hamiltonians in quantum mechanics. I think Pragya will speak about some other cases where different ensembles are natural, but now these standard ones. H0 plus parameter x times h1, parameter y times h2, parameter z times h3, and x, y, z is the parameter space. You calculate the curvature, it's a vector in that space, and you ask, what's the probability distribution of the length of that vector? Okay. Well, it's a long calculation. I mean, it's a whole lecture to give it. It's not an easy calculation. But it's different for n equals 2 and for n equals 3 or more. And there's a physical reason for that difference. In that formula involving the energy denominator, you have the difference between your state and the others. Now, the most important difference is with the neighboring states. If it's 2 by 2, there's only one of them. But if it's 3 by 3 or more, there are 2 neighbors. That makes the difference. Okay, so here we are. We have these are the distributions. And by codimension, a very powerful codimension argument, saying that you will always get, whatever the statistics, whatever the distribution, the probability of getting a large curvature is 1 over curvature to the 5 halves. N equals 2, a nice simple formula. N equals, N equals, this is a distribution which, as you see, is very non-Gaussian. So you can't simply describe it by its mean. So there are different ways. Its maximum is at 1/10. Its mean by construction is at 1. Its logarithmic mean is at 0.3679. So, you can't, it's not simply described by its mean or by its mean and variance as a Gaussian would be. Greater than 3, there's a scaling, a universal function, E0, but the scaling is with the mean, which depends on n by n equals 3, 4, 5, whatever. And here's the function. It looks complicated, but actually it's inevitable. This is the simplest possible isotropic model. Again, the distribution, at the origin, for large C, again, you see the 1OC to the 5 halves as predicted. And again, its mean and its maximum and its logarithmic mean are very different numbers. This was a difficult calculation, and there's an approximation in it. And it was very important to test it, because it's not obvious when you do you get formulas like this, it's not obvious you've done it right. So you have to simulate. So 10,000 sample Hamiltonians, and calculate the curvature for each of them, and the degrees very well. So we know that we didn't make a mistake, because any mistake with those complicated numbers would instantly reveal itself as nonsense in the calculation. So that's a good thing. Now, only wimps study only the general case. Real scientists explore examples. I've adapted this quotation from the numerical analyst Beresford Harlan. And I want to go in some detail through an example to see what happens when you move away from the adiabatic condition, because it's important. We want to understand slowness, and much later, we want to understand slowness in more detail. But so here's this special case. The canonical example is a 2-state system spin half. Here it is. 3 parameters, x, y, z, a Hermitian matrix. Non-Hermitian is another story. Very interesting, but not to be discussed today. And the eigen values are simply the length of this vector, R. And these are the 3 matrices. Here are the 3 Pauli matrices. It's traceless. Trace is just a complication that doesn't add anything. Good. And as you know, all of you probably, it's the original calculation, that the geometric phase is half the solid angle, plus or minus for the two, I should probably say minus or plus, for the two states. For a general spin states, it's a state of Z component M of the spin S particle, it's M times the solid angle. Very good. Excellent. Now, in general, this is a complex Hermitian matrix, no time reversal symmetry. We learned about time reversal earlier. But if you do have time reversal symmetry, you can always represent this by a real symmetric matrix. And then there are only two parameters, and degeneracy is a codimension 2. And once again, it's the length of that little vector in the plane, the eigenvalues. And then you have this situation with the conical intersection. The energies above form a conical surface, double cone in the above or and below the XY space. And it's now a topological phase. It's pi if you enclose the degeneracy and 0 otherwise. And you can think of that in the full three-dimensional story as the flux through a hemisphere, which is a circuit, a surface whose boundary is this circuit in the plane, so a hemisphere of the curvature, and that's where the solid angle, half the solid angle of that is pi, because a hemisphere has solid angle 2 pi. Very good. And this case is the optical anticipations, biaxial crystals, are real symmetric. If you add chirality, it becomes complex Hermitian. It's in optics. Very good, and there's a lot of study of that. Now, beyond adiabatic, you drive these parameters as a function of time, and you do it slowly, but you don't do it so slowly that, you can just go straight to adiabatic. So this is, I think, the simplest non-simple problem in physics, in quantum mechanics. Two-state evolution, a neutron spin, for example, for which the magnetic field is this R vector is changing rather than cycle. So here you have the Schrödinger equation. Epsilon is slowness. You could incorporate epsilon in the parameters if you want by putting it in the T there, but it doesn't really matter. Good. Long story. There's the slowness. Vector of Pauli matrices. I'll put a half to simplify things. Now, the direction of your, call it magnetic field, has a length. It has a length and a direction. Unit vector, E. That's very important. And that's a unit driving vector on a sphere. There it is. It's very convenient for this case, and there are generalizations due to Majorana, but never mind, spin half. Very convenient to represent the quantum state, and you can do it almost completely for this two-state system by the expectation value of the spin. That's a unit vector, as it happens, and it's very convenient. And the Schrödinger evolution is equivalent to a classical spin precession, involving the rate of precession is the length of the vector divided by epsilon. So it's fast precession, but the direction about which you precess is given by the unit vector. Prime is time derivative. Now, the slowest adiabatic approximation is that the spin is following the driving Hamiltonian, the E. And then the spin, another way to say that is, back to the Schrödinger, it clings to an instantaneous eigenstate of this Hamiltonian factor, E dot sigma. And, but you can go further, of course. You can do superadiabatic perturbation series in powers of epsilon, see what happens. And very interesting things happen, unexpected things. It's like WKB for psi. So you can represent the spin expectation, which represents a state, as a perturbation series, starting with your driving direction. Good. And then the nth approximant is taking n plus 1 terms of that and see what happens. Now, I want to have an example of an example. It's easier. You can write general formulas. There's famous, what used to be called Landau-Zehner, but actually it's Landau-Majorana-Zehner, because in the same year, 1932, Majorana published exactly the same idea, is you let your vector go from, it's always an offset of the x-axis, and y is 0, let it go from minus infinity z to plus infinity. So you're just passing by the origin with an avoided crossing of the eigen. So the distance is the square root of 1 plus t squared. And here are the first few of these, successive approximants, successive contributions multiplied by powers of epsilon. So there they are, okay. Well, how good are they? Well, let's look at the distance between the exact evolution and your nth approximant for different levels of approximation. Now, what happens is that these errors decrease exponentially as you add more and more terms. This is for negative times. You're going up past your negative times. Very good. So what you expect from a series. It behaves nicely. However, look what happens at positive times. I've chosen epsilon's point. It doesn't matter what you choose. Then there's no improvement, or hardly any. Very complicated things happen as you once you've passed the origin. So the origin is something bad. Something's happening. Well, and the series actually diverges. You can show that because the higher, there's a reason. You know, it's another story and it's half my scientific life, but convergent series are boring things. Most series in physics diverge, and they do it because the series come as successive approximations, and most of the approximations, WKB, stationary phase, steepest descent, are local approximations. So higher terms involve more and more non-local, which is more and more derivatives of something. And it's an old result of Darboux that the high derivatives of something, the smooth one, typically decay factorially because they depend on the nearest singularity in the complex plane of whatever variable you have. So you actually expect divergence, and you do get it. And here indeed, look at negative times when things look as though they're good. I've taken epsilon equals 1, but you can take any small epsilon you like. T is particular time minus 5. And here are the successive approximations, round to about the 15th. They look as though they look good, but then they diverge logarithmically. They actually diverge factorially as it happens. It's inevitable. By the way, it is inevitable because what you will have, of course, are transitions from your state to the other states. And what that means is that at positive times, your spin experience will be just circulating weakly around the North Pole. But these are exponential, they're beyond all orders. And in fact, every single, this is not captured by this superadiabatic theory because every single approximant, they all, of course, start at down minus 1. They all end up at plus 1. So if you take this seriously, what each term predicts, you would say there are never going to be any transitions. There are transitions, of course, so the series must diverge in order to have its revenge and tell you that you have... I put it in a different way. Things happen in the world because of the time-dependent Schrödinger equation, and they happen according to transitions. If transitions didn't happen, things would never happen. You'd stay in an eigenstate. So the fact that things happen in the world implies that these types of series have to diverge. And I've explored that in detail in other work not to be discussed today. Well, how closely does successive approximants cling to the exact when you go past the origin, past the 0 time? Well, then you answer the question, how and when is a transition born? Now, you explore this by looking at the transition problem, the exact evolving transition probability at different times, but the transition between states depends on how you represent the states. And you represent the states by the nth superadiabatic approximation in this sequence. Good. And so here it is. This is the definition of transition probability. if there were no transitions, this would, of course, be 1, the adiabatic approximation. At minus infinity, it's 0. At plus infinity, you know what it is. Landau, Majorana, Zehner calculated it. It's exponentially small in slowness. So how does that show itself? Well, in lowest order, you just represent the state by the instantaneous eigenstates of your Hamiltonian. In lowest order, then you start at 0, but you end at e to the minus pi on 2 epsilon, that's 0.2, e to the minus 5 pi on 2. There's a slight change, but in getting there, you go through this very large series of oscillations. Large, but still compared to the exponential smallness, but still small compared to 1. Good. A large fluctuation en route to the weak transition. Well, now you do the same thing. You try to see the purpose of these superadditive is to cling closer and closer, epsilon to the n closer to the exact evolution. So what happens? Okay. So here are n equals 0, 1, 2, 3, 4, clinging closer, 5, 4. Look, you're now, you now go from the 0 to your final exponential. The scales are magnified each time with fewer and fewer variations. And once you go beyond the minimum, in this particular case at n equals 4, you then start to diverge and you get nonsense. But what's this here? Okay. Optimal truncation is the representation in which the transition occurs most smoothly. It occurs near 0, the closest approach to the degeneracy. This is the Stokes phenomenon of asymptotics. It's the birth of small exponentials, the transition, the other state, amplitude, when hidden behind large ones. You can always write these 2x2 problems. If you eliminate one of the states, there's a second-order differential equation depending on time. Then you have 2 exponentials, of course, representing the 2 states, and there's this general phenomenon to do with divergent series, which Stokes identified and we understood in enormous detail in the 1990s. It continues to be at the heart of asymptotics now with applications in string theory and non-perturbative quantum field theory. Small exponentials are born when they're maximally subdominant compared to the other exponential, in this case is the state that you first started in. So, and it turns out that the birth is universal. There are some little fluctuations which we know about, and this has the form of an error function, and the width is the square root of epsilon. There's a universal scaling function describing in detail how the small exponential appears. And in this case, there isn't a degeneracy for real time. Of course, you avoid it, but there is a degeneracy for complex time. And it's the nearest degeneracy from this degeneracy in complex time, in the complex time plane, there comes a Stokes line where the 2 exponentials are maximally disparate. And that's where, when it crosses the real axis, where the transition occurs. I call this real physics in the complex plane. Okay, I mentioned it there. And one way to understand how it happens, and I'm not going to go into it now, is if you take the formally exact divergent series and all of the stuff beyond the least term, you can formally sum it in a careful way, then it's from this divergent sum that the second exponential, which is the transition to the other state, is born. So it's born out of the three-sum tail of the divergent series. So that's how and this is a very general idea. Very good. But where's the phase? We've forgotten about the phase in all this. Well, you can define the phase as the phase of the actual state with respect to the local driving Hamiltonian direction, the phase of that, and that has a overall dynamical, it has a geometric part, and the geometric part, there's a formula for it, which I won't give you, but after, well, I will actually, it's this, round a cycle, it's that, and that's exact, but if you write psi as a WKB approximation coming from this what I've described earlier, then you get a series for the geometric phase, and the first term is independent of epsilon, that's why it's geometric, and then you get all the corrections. And you can actually think of them as directions too, if you make a series of transformations to moving frames, moving with the driving Hamiltonian, and that I discussed long ago. So we understand this. We understand this non-adiabatic aspect of the phase. So the series for the state generates a series for the phase. I won't go into it. Now we come to the difficult part. Of course, these parameters, which one forcibly changes in order to create the cycle, to get the geometric phase, these phases are, of course, themselves dynamical parameters. And often this doesn't matter. I mean, when you have a magnetic field produced by some piece of apparatus and you change it, you don't talk about the dynamics of the parameters, but they are dynamical variables. It's just not important. But in some cases, it is important, and the phase must react back on them. You're not interested in the reaction of the phase back on your hands when you twist the sequence of polarizers. But some cases it is important, in molecules, for example. And there you've got nuclei which are slow and fast, and you can think of their positions, slow, as being the parameters determining the quantum mechanics of the electrons, which are light and therefore swift. Okay. Now, everyone uses the Born-Oppenheimer approximation because it's too difficult to usually to solve the full quantum mechanics of a molecule on a computer. So what you do is you assume that the nuclei hardly move while the electrons solve their Schrödinger equation and determine their instantaneous energy levels, which depend on the positions of the nuclei, and that gives you a potential. And that energy of the electrons is, they call it a potential surface, and that is the surface in which the nuclei move, and their quantum mechanics has to be solved to give you the vibration-rotation levels of the molecule. So this coupling, or the decoupling to some extent, is very important. And it depends, of course, on a separation of time scales, slow and fast. Now, it's threatened when electron energies get close to each other, because you want the transition between these levels to be fast. That's when the adiabatic approximation is good, compared to the movement of the nuclei. When the levels get close, energies are close by the uncertainty principle, so the transition between them are slow, and that threatens the adiabatic approximation. But you know that degeneracies are precisely where geometric phases originate. Good. So here's an example that we've actually studied. Here's sodium-3, a 3-nucleus molecule. And here's a cycle in the space of shapes of the nuclei surrounding a symmetrical shape where you have a degeneracy of the electron states, the Born-Oppenheimer states. And the electrons gain a geometric phase of pi, no time reversal. You have time reversal symmetry, no real symmetric, real symmetric matrix. And that means that this must be compensated by a pi phase shift in the wave function of the nuclei. So the whole quantum state of the whole system is single valued. Very important. Well, that shift affects the quantum spectrum of the nuclei. In a simple case, it means that instead of the energy levels, let's say, being proportional to 1, 2, 3, or n squared, let's say, proportional to n plus a half squared. There's a half integer quantization of the electron state of the nuclear states. And that's important. It's seen experimentally. It's very complicated, this spectroscopy, but you can't index the states. It's called pseudo-rotation, this cyclic change of shape. Parts of the spectrum, the complicated spectrum of sodium-3, can only be indexed if you have half-integer quantization. You can't do it if you have integer quantization. Very good. But pi is a special case. It amounts to a reversal. You know, the pi just a change of sign. More general geometric phase also reacts back on the slow physics that drives it. And that reaction is the first step beyond Born-Oppenheimer is the force of magnetic type, geometric magnetism, on the slow variables proportional to their speed. That's reasonable. I mean, you first neglect the speed and then you have it proportional to the speed. Very good. What is that force? It's actually the curvature. So that reveals the dual role of this mathematical object, this central object, the curvature. It not only gives you the geometric phase through its flux, but it acts as a magnetic force, look of the same structure. It's a V cross B, where B is the curvature, correcting Born-Oppenheimer force, acting on the slow variables. There are a number of different examples of that in different areas of physics. For example, the polarization-rotation phase of light. If you have a coiled ray, coiled in such a way that it's now free to move, so you have an optical fiber, this experiment was done, so it's now free to move. The parameters are the position variables of position along the fiber, and the polarization is driven by it. The position reacts back, and geometric magnetism shifts the ray sideways, and this was observed. It has different names: spin-orbit effect of light, optical Hall effect, optical Magnus effect. Different names of the same thing. I prefer the term geometric magnetism because it describes the whole class of these phenomena. Now, this mutuality, the driving of the fast by the slow, the reaction of the fast on the slow, reveals something about the geometric phase. It's an artifact. A geometric phase is an artificial thing. It's an artifact of our decision to treat a system in terms of two interacting parts rather than a whole. Now, you do it for convenience. It's an unquantum thing to do. You know, we always say quantum is a holistic theory. It's an unquantum thing to do, and you could, in principle and occasionally in practice, treat the electrons and nuclei in a molecule on equal footing, and then you can predict everything, spectra, chemical reactions, without ever considering the phase. But treating a molecule as a whole is conceptually, computationally difficult, so the separation of parts is a useful artifact. But more than that, this heavy light discordance, fast, slow, is very natural because it leads to a physically understandable picture. So geometric phases are artificial but useful in exactly the same way entanglement is artificial and useful. Entanglement isn't a fundamental feature of quantum mechanics. It's an artifact of our choice to say, this system has parts. Sometimes it's natural to think of the parts as particles, but you don't have to. You know, this is the well-known sensitivity, dependence of entanglement on the basis you use. Because the whole system, you can solve it, you never talk about entanglement. So it's a similar thing. Now, more generally still, you can't do science without separating the world. You know, we all know that if you try to understand the universe as a whole, it's nonsense. Isaac Newton understood this. He said the following: to explain all nature is too difficult a task for any one man or even any one age. It's better to do a little with certainty and leave the rest for others that come after than to explain all things by conjecture without making sure of anything. Okay? I remember I used to have a toy called the Levitron. I actually spoke about it in Bangalore many years ago. It's a levitating toy. I called the toy Levitation Without Meditation. And when I went to a shop and I saw it, I was fascinated, and I started speculating. This is like a trap for microscopic. And the salesperson said, "Oh, we're not interested in these details. We like to understand the universe as a whole." The American expression is airhead. Okay, so you have to separate to do science. And so one minor aspect of this separation is entanglement, another one is geometric phases. Okay, so that's natural. But it's an approximation. The geometric phase is an approximation in the way I've described it for driving slow compared to the fast oscillations geometric magnetism is the first reaction beyond Born-Oppenheimer. Now, beyond the approximation, both the phase and the forces of reaction include infinite series of corrections. I've talked a bit about the ones for the phase. For the reaction, it's mathematically enormously more difficult. Pragya Shukla, I've written a long paper about a special example of this. It's difficult for a technical reason. You see, if you think of the phase, you prescribe the parameters, the corrections involve successive time derivatives. The first involves velocity, acceleration, rate of change. But if you go to dynamics, even classically, if you have a reaction force that depends on the acceleration and then the rate of change of acceleration and others, you get more solutions than you actually have. It's a well-known redundancy. So you have to have a series of recursive resubstitutions. It's actually very complicated to get reaction forces that still depend only on position and velocity. You can do it, but it's extremely complicated, and there isn't a general theory how to do it to get the high orders. But there's a lot of evidence that in most cases, these series of corrections would actually diverge. Now, what does it mean when the reaction force does? It casts doubt on how strictly the fast and slow variables can be separated. That's the separation of the world in my title. Even in classical physics, it's a difficult problem. So we don't know whether, by some clever resummation, you can strictly separate the fast, and you can get effective dynamics for the slow system without having to consider the dynamics of the fast system explicitly. It's complicated. I'd say there's a series of correction terms, and we have them, and behave well enough, the series, however, diverges, but we don't know, strictly speaking, whether one can, to all orders of slowness, separate the fast and slow. And that's a deep problem. It's a special case of the bigger world of system environment problems. You know, sometimes the environment is perturbative, is weak. Sometimes it provides disorder. You trace over it and that gives decoherence. Here it's slow. It's another class of systems of that, problems of that kind, and we don't know the answer to it. There are a lot of papers where people talk about geometric magnetism, and some where people go a little bit further and consider one or two correction terms, but nobody discusses the full structure and what it means. You know, if you're interested in divergent series as I am, then this is a tricky series of special cases. We don't know the answer to that. Okay, now, I come to a timeline of this problem, this geometric phase phenomenon. 1831, Hamilton-Lloyd, the pi phase in conical refraction. 1924, Bortolotti showed that Maxwell's equations imply that in the geometrical optics approximation, polarization is parallel transported along curved rays. This was rediscovered by Rytov in 1938, and it led Vladimirsky in the year of my birth to realize that parallel transport would imply a polarization transport after a curved ray returns to the same direction. That's the spin redirection phase. He said, I don't know how to make a ray do this. He didn't have optical fibers. Of course, later that was done, but that was Vladimirsky. And he had the solid angle formula as well for that. 1956, of course, Pancharatnam. We all admire him. I'll come to that in a moment. So Pancharatnam, he, as we heard this morning, understood the geometric phase is for two-state systems in the context of polarization optics. He included the natural connection and the solid angle on the Poincare sphere. Longet-Higgins, Price, Erpig, Sachs, the first step beyond Born-Oppenheimer in molecules, they realized that the pi phase change of the electrons must imply a change in the spectra of the nuclear states. They were in Bristol at the time. Maurice Price was the head of department. 1959, Aharonov and Bohm, also in Bristol. There's no evidence that they talked to each other about this. they discovered what we now can understand as a geometric phase for electrons from an inaccessible line of magnetic flux. 1975, in radio wave physics, Budd and Smith were describing radio waves in the ionosphere. They have a complicated polarization state, and you can make a geometrical optics type approximation of the rays and the corresponding waves. And they found something to their surprise. They knew, of course, that they had to include the phase along the ray. They called this phase memory, the integral of the local refractive index along the path. But then they found something which they called additional phase memory. And that's exactly the integral of the one form, which for a circuit is the geometric phase that we've been discussing. And they had exactly the formula for this one form. They were a little bit puzzled by it, but they drew attention to it, additional phase memory. 1979, Mead and Trullard in chemical physics, they generalized Longet-Higgins by understanding that what we now call the two form, the curvature, they didn't call it that, acts as a magnetic field on the nuclear motion, geometric magnetism, and so that was their context. And then my paper, general phase for slowly driven quantum systems. I emphasized the importance of circuits, more of that in a minute, and the underlying curvature especially, and the fact that there's a natural origin in the Schrödinger equation, okay? Oops, excuse me. Then, oh no, sorry, I missed out a page. Very important. Let me go back to an earlier, in 1983, Barry Simon made a collection with fiber bundles in the Chern class and with the quantum Hall effect. There had been a paper by Thouless and colleagues a year before in which the curvature, as we now call it, had appeared. And Barry Simon made that connection with geometric phase. His paper was published before mine because the referees lost it. And it appeared, and because of the way the calendar went, it was a year later. I'd shown it to Barry Simon, and he made this mathematical connection with, as I say, with fiber bundle, a disease he called bundle fibrosis. Okay. Then came Wilczek and Z. Now, an assumption not mentioned is that the states are discrete, and then the adiabatic theorem means that the state returns. If the states form a continuum, you can have cases where a little degenerate subspace returns to itself, maybe separated from the others or for whatever reason. And then when that degenerate subspace returns, you have something more general than a phase. You have a little matrix which determines the possible phases and transitions between the states in that little degenerate subspace, and that's determined by a Wilson loop. It's a more complicated thing. It's a time-ordered product of successive states as you go around the loop, and that's called the non-abelian phase. That's an important generalization. Well, then came my colleague John Hannay, also in Bristol. He realized, he thought there must be a classical counterpart of this, and indeed for non-chaotic classical motion, you use action angle variables, and he showed that there are angles which have a shift corresponding to the geometric phase. It's now called the Hannay angle. The Foucault pendulum shift is an example of that, and I made the connection about the same time from his idea. Connection with the quantum phase. One is the derivative, the other with respect to the action. You can show that. Then Aharonov-Anandan removed the slowness restriction. Now, this is important, and Professor Mukunda emphasized it, but I would emphasize it in a different way. I found it interesting, but I didn't find it fundamental, because I asked the question, how do you make a state return? It's often very difficult. Now, one way, of course, is to do it slowly by changing parameters. Then the Hilbert space description becomes the parameter space description. And for a long time, I thought of it as artificial because I didn't know a general way of making states return to themselves. There are some special cases you can write down, but which they did, but they're very special. However, about 11 years ago, in a different context, I realized that there is a prescription for making quantum states do anything you want at any speed, that is, without going slowly. And the way it works, I wrote this paper called Transitionless Quantum Driving. The way it works is that you have the eigenstates of a given Hamiltonian, and you want them to return without any transitions between them after some time, which can be short. The way you do that is you drive them with a slightly different Hamiltonian, precisely described, coming from the Hamiltonian whose states you're transporting, and that guarantees there are no transitions between the states of the first Hamiltonian. It's a kind of reverse engineering of the Schrödinger equation. And it has had, although actually it turned out that the formalism I developed was earlier published by Rice and Demiplak, it doesn't matter. The fact is you can do it. And now it no longer is so artificial, because I know how to make any series of states move cyclically, okay, as Aharonov-Anadan wanted. So my objection that it was artificial has slightly gone away because I now know how to make it happen. It's a different, and it applies in various fields. People, for example, in laser cooling, people have done it adiabatically, but they'd like to do things quickly, but not have transitions. And there's a whole world of problems of this kind, which I don't have time to go into. Okay, just to mention, I've mentioned Bristol a number of times. It turned out, and none of us realized it until the 1990s, that there's this common geometrical thread running through the physics in my department, due actually to the genius, the way of thinking of Charles Frank. And I just want to mention a few more. There's Charles Frank, who understood dislocations in crystals, the Berger circuit, as an anholonomy. He considered going around a dislocation and mapping what you do at every point to making transitions in a perfectly undislocated crystal. After your circuit in the dislocated crystal, there isn't a circuit in the there's a gap. That's the Berger's vector. It's pure anholonomy. He did the same thing with disclinations in liquid crystals. John Nye and I realized that you have phase singularities in general scalar waves. Special cases considered before were vortices in superfluids and quantized flux lines in superconductors, especially around which you go around and the phase changes. It's actually 2 pi, but it's still a phase change. That's anholonomy. That was earlier than the geometric phase. And John Nye himself talked about polarization singularities in general vector light. He just died a few months ago, just before his 96th birthday, still working intensely. Okay. Now, I'll go back to my other lecture now. Excuse me. Sorry about this. There's a reason why I want to, because I haven't quite finished. Right, let me go back. Now, just to say, okay. Now, what do you call this damn thing? There is, in physics, a convention of naming things after people. Okay. Now, sometimes we all do it. We talk about the Schrödinger equation, Hamilton's equation, whatever. So perhaps one should call this the Hamilton, Lloyd, Bortolotti, Ritov, Vladimirsky, Pancharatnam, Long, Higgins, Price, Erpik, Sack, Aharonov, Bohm, Budden, Smith, Bede, Drouillard, Berry, Simon, Hannay, Wiltshire, Aharonov-Anadan phase. Well, you can argue about the names. Bargmann, I learned about Bargmann recently. He never mentioned phase at all, so that's why I don't include him, although it's very deep what he did. Samuel and Bandari, Mukunda, Simon. I want to talk about, just briefly, if you forgive me, not being enthusiastic, about the phase for incomplete cycles. People started to ask me, when this phase became popular, do you really need a circuit? And I said, well, of course you don't. You could stop, but then you have to close somehow. You still do need a circuit, and a very natural way is a geodesic in the space of parameters. I didn't think that was worth writing because I thought it was kind of trivial and obvious. Then when the Hilbert space framework became popular, it was obviously, it would be a geodesic, and generally it's the Fubini study metric. And so when your paper came, so I thought it was very clever. I mean, the technical way you did it, but I didn't find it deep because you still have a circuit. It's kind of artificial. It seemed obvious that you close it along a path where the integral of the one form is 0. So that's why I didn't mention it. It doesn't mean I disrespect it, but I just want to tell you why I didn't include it here. It's a little detail. Okay, that's eponymous nomenclature. But there's another way of talking about things in physics, which is to describe them by what they are. And in this case, of course, the descriptive nomenclature is the geometric phase. And of course, it's obvious what I prefer. So I like to describe it, avoiding all the... But there is an interesting history, and it goes back a very long way. It involves a lot of people, and none of which, the ones before 90, none of which I knew about when I found the phase. And this is wonderful to find people kept discovering more and more my distinguished predecessors, and I don't think of that as any way disappointing. It's just wonderful to learn about the way in which an idea has either been glimpsed, or in Pancharatnam's case, and Budner and Smith's case, a bit more than glimpsed, in one's earlier work. I didn't know about Pancharatnam. I found out about when I came here, and Mukunda knows this, it's something in 1986, and I spoke about the phase. It was popular at that time. And afterwards, Rajaram and Subhro's Ramasation came to me and said, do you know this Pancharatnam? I said, no, I don't know anything about Pancharatnam. And they told me, and I didn't understand it. And on the plane home, I very carefully read their article about what Pancharatnam was done, and I realized how wonderful and interesting it was, and how it's kind of, for the case of these two-stage systems, parallel, anticipating many aspects of geometry. And I wrote a paper about it. Pancharatnam's phase, giving a name, geometric phase, not giving a name. And then I learned more about Pancharatnam. Ramasation gave me a copy of his collected work, which I treasure. And there were so many beautiful things. And he died so young. So I never met him. I regret that. I met his widow, Prema, who still lives in Oxford. But to very sad, that's a little bit of history. Now, back to the beginning. This is the last part of my talk. There's a very easy way to see Hamilton's cone and its geometric phase. So this is do-it-yourself conoscopy. Some of you have seen this, but there's something new. You know, traveling through a crystal, the thin slab of crystal, phases, the waves get out of step. This is a simple way of, see, Hamilton's is complicated. You need a long crystal to get a big circle, and it's hard to get one free of defects. It's a long story. But you can, with a thin slab, you use interference, and what I call a black light sandwich. You have two crossed polarizers, and and in between you put this biaxial crystal. Well, we don't have biaxial crystals, us theorists, but there's something else which I learned from Rajendra Bhandari, one of my visits here. The old overhead projector transparency foil is biaxially anisotropic for reasons that my polymer physicists tell me is obvious, but nobody ever thought of it before. We used this stuff for 30 years to give our lectures, didn't realize that they had this wonderful property, but it's revealed in this way. So then you just look through it. And Rajendra Bhandari, Susanna Klein, I wrote a paper about this particular way of seeing, well, I'll show you now. You just look through it. See, what is looking? Looking is not straightforward, but roughly speaking, looking is directing your gaze in a given direction. So you're seeing at each point in the field of view, this is in front of your camera, the light which has come from different directions, and you have a cone, and your position on the cone to determine where you're looking, and you're seeing interference. These are contours of the separation of the two cones in direction space. And that's what the internet called color dependent, because it's waves, and it's not monochromatic. Now, it turns out that that's the fringes, but this black stripe is the geometric phase. It would be a cross if you had a phase of 2 pi, and that's the case of a uniaxial material where the two optic axes come together. It's a crystal of higher symmetry, excuse me, and it's used by mineralogists, the fact you get a cross, to you can understand the stripe by thinking of the way the polarization states change as you go around. Never mind. The cross, they use it to distinguish uniaxial biaxial materials. one other nice thing, it's not to do with the lecture, but it's a nice thing, is this. Imagine each point here on this picture is described by a little 2x2 matrix. Electric field comes into the slab, EXEY, comes out of the slab, EXEY, a little 2x2 matrix. All of the matrices corresponding to any point here, and actually anything you could put inside, have the lovely property that they're non-trivial square roots of 0. You can think why, it's kind of physically obvious. You know, the square root of 0, if it's a number, is just 0. But there are matrices, A, B, C, D, which when you multiply A, B, C, give you 0, 0, 0, 0, and there's a whole infinite class of them, and this instantiates this object. So when you look, and Mark Dennis and I wrote a paper about it. Now, we were, you know, you can take this picture from many places. This is a place near where Stokes was born in Ireland, looking out across the sea. It's the same phenomenon exactly. Stokes, of course, whose 200th birthday we just celebrated, and who contributes a great deal to understand his version of the Pauli matrices with the Stokes parameters. You alluded to this. Well, this was finished, but then sometime later, I received a lovely email from 2 Dutch astronomers who said, we've seen this from the trains in the Netherlands. And, well, how is this? Where is the blacklight sandwich? Okay. Well, the first polarizer is actually the sky, the blue sky. The blue sky is polarized, if you look far away from the sun, by the act of scattering, Rayleigh scattering. A few months ago, I had the privilege of visiting the country house where Lord Rayleigh lived. He's one of the rare physicists who was already a member of the nobility before he did science. And I had the great pleasure of visiting the present Lord and Lady Rayleigh, and there is Rayleigh's laboratories. He died 100 years ago. We've been marking that. His laboratories, which we saw unchanged since 1919. Incredible. 3 floors, he remodeled them. It was beautiful. And I held in my hand his papers on Rayleigh, his manuscript on Rayleigh scattering and the polarization of the blue sky. Here we are. Whoops. Actually handwritten. Wonderful thing. Anyway, so that's the first polarizer. What's the overhead transparency? That's the window of the train, which is stressed during manufacture, so that if there's an accident, you don't get sharp splinters of the glass. It breaks up into little approximate blunt cubes. That saves a lot of people's lives. And the final polarizer, like every good scientist, they carry polarizers in their pocket, so they hold them up. And then they see this, and they see this, and I wanted to see my own. So this is in the UK from one of our trains. It's a general phenomenon. It's very nice to be able to see all these nice mathematical ideas. You know, I did once, to students, give a complete lecture about matrices based on this one picture, you know, showing things. It's kind of nice thing, degeneracies, whatever. Okay, this is another picture from one of our trains in the UK. And another. Over the years, I've written a number of papers on this and related subjects. They're all on my homepage. They're all downloadable. I wrote a book a couple of years ago, which is a sort of book of reprints of papers because I've worked on a number of different things, and they're all connected in subtle ways. And so the book has the papers reproduced with permission of the public, but also introductions connecting the different themes. I don't think many people actually have read this book, but at least 2. I have at least 2 readers. There they are. This was sent to me by colleagues who were very pleased to see their daughters. It would be a wonderful thing if these young women would grow to become the physicists of the future. So let's hope that happens. Thank you very much.